In this video, we're going to go ahead and apply the concept of absolute or conditional convergence. So again, the first statement is that if I have something that is absolutely convergent, then I have actual convergency. If I don't have absolute convergence, but I can prove that the original series is convergent, then I can state conditional convergency. It's convergent, but not absolutely convergent. And then finally, or I can prove that it's divergent. So in this particular series, we're going to go ahead and start out with, well, let's just go ahead and test absolute convergence. It's got that -1 to the power of k plus 1. I could attempt to use the alternating series test on this, but again, if I prove that it's convergent, that means I still have to prove that it's either absolute or prove that it diverges. So your goal, if you're starting here, is to prove divergency. If you can prove divergency, then you're done. But if I prove convergency here, then I still have to go one step further and prove absolute. So I'm going to go ahead and just straight up start with the absolute convergence. So I'm going to test whether or not this series is actually convergent. So in this series, we're actually looking at this series because the -1 to the power of k plus 1 inside of an absolute value doesn't change anything. And actually, more importantly, the absolute value of k squared doesn't change anything. So this really just becomes 1 over k squared. But I know this to be a p series with p greater than 1, which implies we have a convergent series. So let's be very specific about this. This is a p series that is convergent. This p series is equivalent to the absolute value of the original series, so therefore I can state that this is absolutely convergent, and therefore I'm done. Again, it's not a heavy process. It just adds a couple extra layers to this problem. If I can prove absolute convergency, I'm done. If I prove that the absolute series is divergent, then I have to go a step further, because the fact that if I prove that the absolute value of the series is divergent, then I haven't proved that the original series in and of itself is divergent. So let's go ahead and dive into another example in terms of a possibly more difficult problem. If I have k equals 1 to infinity of -1 to the power of k plus 1 all over the square root of k, this is my new series. If I consider absolute convergence first, and again, that's what I'm always generally going to start with. I'm going to consider absolute convergence first. Again, you don't have to start with absolute. You can attempt to try and prove divergence right off the bat, but I'm going to go ahead and start with absolute. With the absolute convergence, I'm going to have k equals 1 to infinity of the absolute value of -1 to the power of k plus 1 divided by the square root of k, all inside the absolute value. I know that this is going to transition to the summation of simply 1 over the square root of k, because the square root is positive always, and the absolute value doesn't need to be on that, and the square root of an absolute value, or square root of -1, just becomes 1. So now I'm left with, once again, a p series, but this time p is between 0 and 1, which implies we have a divergent series. So what does this tell us? Let's be very clear about this. I know for a fact that this is not absolute convergent. That does not tell me anything about conditional, and it doesn't tell me anything about divergent. So I'm going to go ahead and do this. I'm going to say not absolute convergent, check. I'm going to put a question mark here on conditional and a question mark here on divergent, because I don't know. It could still be conditionally convergent. It could be outright divergent. So let's go ahead and then start talking about the original series. So let's look at this thing right here. I can attempt to try and apply all different types of methods to it. I can apply the div test, but I think since it's already a -1 to the power of k plus 1, let's just go straight with the alternating series test. Now, it is important that when you're doing these problems that you actually write down what method of evaluation or test or type of series that you're looking at you're actually working with. The important reason why that is because anybody who grades these assignments, they're going to want to know what you're trying. So the alternating series test tells me I'm going to look at 1. 1 is going to be a sub k is equal to 1 over the square root of k, and I want to make sure that that thing is always, again, non-increasing. So a sub k prime is actually going to be something like the -1/2 k to the -3/2, because we're going to drop down the power and subtract 1 from the power. This becomes, again, the same exact concept. It is always non-increasing. Number 2, we take the limit as k goes to infinity of 1 over the square root of k, which gives me equal to 0. That's the second piece that's identified. So I can conclude that this is an alternating series, and the test proves that it's convergent. So if the original series is convergent and it is not absolutely convergent, then I can say that it's conditionally convergent, and I don't have to test divergency. So again, it's important that you actually have to check more or less all three details. You have to either prove absolute convergence, and then you're done with it's not conditional, it's not divergent. Then you have to, if you prove that it's not absolutely convergent, you still have to prove that it's conditionally convergent, or do the step that it is divergent. And this is the process on how to work through these problems.